Hello friends, today we will have a detailed discussion on Sn1 reactions. We will consider the mechanism, stereochemistry and all other allied aspects of Sn1 reactions. That is the most important part of these nucleophilic substitution reactions at an sp3 hybridized carbon atom here. Okay, so in a general nucleophilic substitution reaction, say for example, say Rx, it is an alkyl halide here. So this is reacting with a nucleophile. Okay, this is giving you RNU plus X minus here. So X minus, that is a leaving group here. Rx, that is an alkyl halide containing a halogen atom. Okay, halogen atom bonded to a carbon atom here. So nucleophilic substitution reaction at an sp3 hybridized carbon atom here, it involves two sigma bonds. Okay, the bond, with the leaving group, that is a carbon with the leaving group, it is broken and a new bond with the nucleophile RNU, it is formed here. This bond is broken and this bond is formed here. So the electron pair in this RNU bond, it comes from the nucleophile here, because this X, that is the leaving group, it is departing with the electron pair in the bond, Rx bond here. Okay, now to understand the mechanism, we have considered all these aspects in the previous class. To understand the mechanism of this reaction, we should know the timing. So which activity takes place first? Okay, or whether these two activities, like the bond breaking and the bond making, all these activities take place simultaneously. That is one aspect. The second aspect is whether bond breaking takes place first, followed by the bond making, or the other way around. That is, the bond making takes place first and bond breaking takes place subsequently. Okay, now we have seen a reaction mechanism that bond breaking and bond making take place at the same time. That is the Sn2 mechanism. We have considered that is a one-step mechanism. We have already considered that aspect here. So today we will be considering the most important thing is the Sn1 mechanism, that is substitution nucleophilic unimolecular reaction here. For in this reaction, the bond breaking, that is the Rx bond, it is the breaking, it occurs before bond making here. Correct. So this is a two-step mechanism. So let us see how this reaction takes place here. So this is the thing here. Okay, this bond is broken here. So this leaving group, it is leaving with the electron pair here. So we are getting an intermediate here. This is the carbocation intermediate. So this carbocation intermediate, it is reacting with the nucleophile to give this species here. Finally, this is the product formed here. Okay, this new bond, new bond, it is formed here, and the CX bond is broken here. Bond breaking occurs before bond making. It is a two-step mechanism. Two-step here. The first step is the heterolytic cleavage here. The CX bond, it is heterolytically cleaved or broken, and the leaving group, it leaves with the electron pair here. Correct. This is the leaving group here. Okay, heterolytic cleavage here, it is taking place, and the carbocation is formed as a reactive intermediate. Correct. And a new bond is formed. Afterwards, the carbocation is reacting with the nucleophile here. So the rate of the reaction, we have seen, it is equal to K, that is the rate constant, into Rx here. Okay, Rx, it is the concentration of the alkyl halide here. So it is a first order equation. Okay, the carbocation is intermediate here. First step, that is the rate determining step here. That is the first step, the bond breaking take place here. Okay, when the bond breaking take place, that is the first step. That is a slow step in the reaction mechanism here. Bond breaking take place here. That is the rate determining step here. Correct? That is called rate determining step here. So the rate of the reaction here, it will depend upon the concentration of only one reactant, that is the alkyl halide here. So therefore, this is a first order kinetics, okay, unimolecular reaction. First order kinetics, unimolecular reaction here. So let us examine this concept with the help of an alkyl halide. Okay, alkyl halide reacting with a nucleophile. So we will take up an alkyl halide of this nature here, say Ca3 CBr. This alkyl halide, this is reacting with a acetate anion here. Okay, now here the CBr bond will be broken and a new bond with the acetate anion, it will be formed here. Okay, substitution of the bromide anion with the acetate anion here. correct? The Br minus leaves, CBr bond is broken. So we will be getting a compound of this nature here, CH3 thrice C. Then we have a new bond, CO bond is formed here. Then CO, CH3 here, correct? So CBr bond is broken here. So Br minus leaves. That is the leaving group here. Okay, CO bond. This is a new bond formed here with the nucleophile here, correct? So substitution of Br minus by acetate anion here. So the kinetic data here, it shows that this reaction rate depends upon the concentration of only one reactant, that is the alkyl halide here. Therefore, we can say the rate equation is the first order rate equation here, correct? So first order rate equation. So the reaction will be proceeding in this fashion here. So rate will be, it will be depending upon the rate of the alkyl halide here, the concentration of alkyl halide here, correct? So this is the rate of the reaction here. Rate is equal to K into CH3, this is the alkyl halide here, correct? So it is a one reactant appears in the rate equation here. This is a first order kinetics again. First order kinetics. So only one reactant appears in the rate equation, first order kinetics. Therefore, this is known as, and it is unimolecular, correct? Unimolecular. So this is known as Sn1 reaction. Okay, that is this mechanism, it is known as Sn1 mechanism. So the example, we can clearly write here Sn1 mechanism. Say this alkyl halide here, CBr here, okay? So this Br bond, CBr bond is getting broken here, and we have this acetate anion here. Okay, this is the reaction here. So we will be getting CH3 thrice CO, a new bond is formed here, CH3. This acetate is formed here plus Br minus, correct? So the rate here, rate of the reaction equal to K, that is rate constant into the concentration of the alkyl halide here. Therefore, this is the first order kinetics. Only one reactant appears in the rate equation, first order kinetics here. This is the unimolecular reaction. This is the Sn1 reaction here. Substitution, nucleophilic, unimolecular. It is known as substitution, nucleophilic, unimolecular. Okay, now here the kinetics we have seen, the rate. Okay, so the first order kinetics reaction involves more than one step here. That is two-step mechanism here. Sn1 reaction is a two-step mechanism. More than one step is involved. Here the slow step, that is a unimolecular step here. Okay, the slow step, it is unimolecular. It involves only the alkyl halide here. Now, since the concentration of the alkyl halide alone determines the rate of the reaction, rate is equal to K into the concentration of the alkyl halide here. Therefore, what happens here? Nucleophile is not in the picture. Therefore, the identity of the nucleophile or the concentration of the nucleophile, okay, it doesn't have any effect on the rate of the reaction here. Most important point here, okay, it is only is a first order kinetics. Rate depends only on the concentration of the alkyl halide. Therefore, the nucleophile, suppose this nucleophile, I am replacing it with some other nucleophile. Nothing happens to the rate of the reaction. The reaction will proceed. The rate will remain the same here. Now, if I double the concentration of the alkyl halide, what will happen? The rate of the reaction will be doubled because the rate depends only on the concentration of the alkyl halide here. Doubling the concentration of the alkyl halide, it will double the rate here. But if you double the rate of the the concentration of the nucleophile, nothing happens to the rate of the reaction. Nothing happens to the rate of the reaction. It has no effect because the rate it depends only on the concentration of the alkyl halide here. Here the slow step, that is the rate determining step here, it is a unimolecular reaction here. Therefore, this is the Sn1 reaction. It's a two-step mechanism here. So let us see the two-step mechanism in detail. That is, first step here, it will be a heterolytic cleavage of the CBr bond here. Okay, that is step 1 and step 2 we can write here. That is step 1 of the reaction will be, say we have Ca3C, this is our compound molecule here. Okay, now this is Br. So this is breaking here, bond breaking here. This is a slow step here. Okay, this is the slow step. This is the rate determining step here. An important point here is this carbocation. This carbocation has got tremendous role to play in the Sn1 reactions. Important point. It will determine the stability. The stability of this carbocation determines the rate of the reaction and all. We'll learn it later. So this is the carbocation here, and we are getting the Br minus here. Okay, so this is the leaving group here. So this is the heterolytic cleavage, heterolysis of the CBr bond here. This is CBr bond heterolytic cleavage. Heterolytic cleavage means unequal dividing of the electron pair here in the bond. That is, the bonding electrons are taken away by the bromine here, correct? And the carbon is left with nothing. So carbon, it becomes an electrophilic site here, C plus, that is the carbocation here. Heterolytic cleavage of the CBr bond forms an intermediate carbocation. Okay, so the step is the rate determining step, that is the slow step here. Okay, now in the step 2, that is the fast step here. Step 2 is no bond breaking is involved, so only bond making, that is this carbocation. This is reacting with the nucleophile here. Okay, so this is the nucleophile will be O minus here. That is the acetate anion here. So this lone pair, it is getting attached with this C plus, the positively charged carbon atom here. Okay, so this is the fast step here. Only bond making is involved. Okay, nucleophilic attack, the acetate. The nucleophile is the acetate anion here. Therefore, the nucleophilic attack of the acetate anion on the carbocation, it forms a new CO bond here. So CO bond will be Ca3 thrice here. Then we have a C. A new bond is formed here. See, this is the new bond being formed here. Okay, then the rest remains the same thing. COCA3 here. Okay, an acetate, it is formed here. Okay, so the nucleophilic attack of the acetate anion on the carbocation take place. Correct. And a new CO bond, it is formed here. CBr bond is broken and a new CO bond is, this is the new bond here. New CO bond, it is formed here. Okay, new CO bond, it is formed in the product here. Okay, this is the, what is this kind of reaction? This reaction is actually, it is a Lewis acid-base reaction here. This is Lewis acid-base reaction. Why? Because the carbocation, it is an electrophilic carbon, electron deficient carbon here. So that will act as the Lewis acid. Correct. And the carbocation, it is the Lewis acid, and the nucleophile is the Lewis base here. Okay, the carbocation, it is a Lewis acid, and the nucleophile acetate anion, that is the Lewis base here. Therefore, these are the step 1 and step 2. 2 steps we can say in the Sn1 reaction here. Okay, the first step, heterolytic cleavage of the CBr bond and formation of the reactive intermediate carbocation. That is a slow step. That is a rate determining step. Correct. Now, then the second step, it will be the carbocation, it will be reacting with the nucleophile, nucleophilic attack. Okay, on the carbocation. It is a fast reaction here, and a new bond, CO bond, it is formed here. No, here, in the step 2, it is a fast step here because no bonds are broken here, and only a new bond, it is formed here. Correct. Now, if you see the most important thing is, this is the mechanism. Now let us see the energetics here. That will be very interesting. That is energy diagrams. We can draw energy diagram for the Sn1 mechanism here. So energy diagram means we have drawn energy diagram earlier. It will be two coordinates we will be drawing here. That is the x coordinate, and there will be a y coordinate here. So like this, on the x coordinate we will be plotting the energy here. So here it will be energy. And this will be the reaction coordinate here. So let us see how the reaction proceeds here. So this is the reaction between that alkyl halide. So this is the alkyl halide we have taken, Ca3 thrice CBr. So this is reacting with the acetate anion here. CaO minus. So this is the Sn1 reaction. Correct. So we are just seeing the energy diagram, how it will look like. Energy diagram for an Sn1 mechanism here. So let us see. This is the, the reaction starts from here. We have the reactant here, that is the alkyl halide. This is our reactant. Now, you see the first step involved, that is the slow step. We have seen that first step is a bond breaking. So CBr bond will be broken here. Correct. So energy diagram, we can say there are two steps. This is a two-step mechanism we have seen. First step, bond cleavage, and intermediate is formed, and then bond formation. Okay. So each step, it has got its own energy barrier with a transition state here. And the transition state will be at the energy maximum. Correct. Now, the transition state for the first step here, it will be at a higher energy, because first step, it is the rate determining step. That is the bond breaking is involved here. Now, the delta H, that is the enthalpy change. Enthalpy change for the step 1, that will be positive. Why? Because it is a endothermic reaction. Bond breaking is involved here. Correct. Therefore, let us see how this curve can be drawn here. So here the reactants, it will be proceeding like this. It will go here, then it will come down. Okay, I will explain each and every point here. So this is the energy of our reactants here. This line, this is the energy of the reactants here. Correct. So let us draw it here now. Energy of the reactants here. Now this is the activation energy. That is the energy needed for breaking the bond here. That energy barrier, it is to be overcome for the reaction to proceed. We have seen that. So this is EA1. We can say EA1 is the energy of activation for the step 1 of the reaction here. Correct. So this is the step 1. Step 1. So the transition state here, it will be a partial bond breaking will be here. That is Ca3 thrice. Then we have this bond is partially broken here. So this is our transition state for step 1 of the reaction here. Correct. That is the CBr bond is partially broken here. Therefore, there will be a delta plus and a delta minus here. That is a partial positive charge and partial negative charge here. Now, this is the position where we get the carbocation here, intermediate carbocation here. So, Ca3 thrice C plus. This is the carbocation. Okay. Plus here. Now, this is the energy level. We can say this is the energy of the products here. The first step, this is the product being formed, this is the carbocation being formed here. Therefore, this energy difference here, this is our delta H1. This is delta H1. Okay, this delta H1, it is having a positive value because it is an endothermic reaction. Correct. Energy is absorbed for the bond breaking. Bond cleavage is involved here. Now, here, this is the step 2. Step 2, this is the transition state here. So, the step 2 transition state, the new bond, it is partially formed here. That is CH3 thrice C. We can say the new bond, that is O, with a bond O, it is formed here. The rest everything is same here. CO, say CH3, whatever it is, you can write here. Okay, so no problem. So this is important here. The point is CO bond, it is partially formed here. So here it will be a delta plus and delta minus here. Okay, negative charge, positive and negative charge here. So this is the EA2, that is energy of activation for reaction 2 here, EA2. Now we have EA1 is greater than EA2 because first step it is bond breaking is involved, second step is bond formation is involved here. Therefore EA1 is greater than EA2. Now which is our, this is the product line there. Okay, this is the product here, represents the product here. So the product will be CH3 thrice C, then we have a new bond O is formed here, then we have CO, CH3 here. This is the product here. Correct. So this is the energy level of the product here. Now this is the our delta H2 here. Correct. From here the product to the reactant side here we can say. So this is delta H2. Delta H2, it is negative value. The energy of the product, it is at a lower level compared to the energy of the reactants here. Okay, now we have got all the parameters here. We have EA1, we have EA2, energy of activation 2. EA1 is greater than EA2 here. Then delta H, you see delta H1 is positive because it is endothermic reaction, and delta H2 is negative here because the products are at a lower energy here. Correct. Now step 2 is negative because only bond making is involved here. Bond making occurs and energy is released here. Therefore, the overall reaction, it is assumed to be an exothermic reaction here. So this is the delta H overall, I can say here, that is the total enthalpy change or heat of reaction. Correct. So the overall delta H, it is the, that is, this is the energy of the reactants here, starting material alkyl halide, and this is the product here. So the difference in the energy here. Okay, the final product is down at a lower energy here than the starting material. The overall delta H here, it is negative. That is, I will write here all these things for important points here. When you are drawing this energy diagram, say EA1, it is greater than EA2. First point here, energy of activation for step 1, it is higher than energy of activation for step 2 here. Now delta H1, that is an endothermic reaction here, that is positive. The value is positive here. Delta H1 is positive here. Now delta H2, that is the energy difference between the energy of the carbocation here. We can say that the reactant as far as this step is concerned. Therefore delta H2, it is negative here. Correct. Delta H for step 1 is positive, only bond breaking is involved. Delta H for step 2 is negative, only bond making, that is energy is released here. The overall reaction is going to be exothermic. Therefore the products are at a lower energy compared to the starting materials here. Therefore the delta H overall, that is negative. That is the total enthalpy change in the reaction. It is negative here. Okay. Delta H overall, it is negative value. Correct. So this is the transition state TS1 for this step here, and this is the transition state for step 2. Therefore this Sn1 mechanism, it has got 2 steps. Then there are 2 energy barriers here. Correct. So this is how we have to draw the energy diagram for this reaction. Correct. Now let us see Now the stereochemistry, that is very interesting aspect of Sn1 reaction. Stereochemistry of Sn1 reactions. So everything depends upon the carbocation. It's a very important fellow. Carbocation intermediate here, no? So this is the carbocation we have seen there, Ca3C. So this will determine the stereochemistry now. Okay, so what is the shape? That is the geometry of this carbocation. This is C plus. This is an sp2 hybridized carbon. Correct. So sp2 hybridized, because there are three groups only here. Three groups around the carbon, central carbon atom here. Therefore, it is an sp2 hybridized carbon atom here. Correct. Therefore, the geometry, it will be a trigonal planar geometry. Trigonal planar, that is the geometry here. Three groups around carbon atom, the shape, that is the geometry of the carbocation, it is trigonal planar here. Okay, now this will have, we can write it like this here. So central carbon atom here, then one methyl group here, then one methyl group here, we can say on the wedge here, then one will be down the plane here. Correct. Then there will be important point here, two orbitals here, p orbitals here. It will be extending above and below the plane here. Correct. Vacant p orbital. These are vacant p orbital. I can put a plus charge over here. These are vacant p orbitals here. This is extending above and below the plane here. Correct. Therefore, trigonal planar carbocation, it is formed as a reactive intermediate in an Sn1 reaction. Now let us consider a reaction here. Let us see how the nucleophilic attack takes place and how the geometry of the final product, it is formed here. Correct. Now, to understand the stereochemistry, the most important point here, we should have a stereogenic center. Correct. We should have a stereogenic center. Then only the stereochemistry can be studied here. So we will take up a tertiary, alkyl halide here. Let us see a stereogenic center. We will find out here in a 3 degree. We can say a tertiary nucleophilic substitution reaction of a tertiary 3 degree. We write like this, alkyl halide. Okay, the central carbon atom will be a stereogenic center. That is a leaving group. It is bonded to a stereogenic center. That is a stereogenic carbon atom. Leaving group is bonded to a stereogenic carbon atom. That is most important point here. Then to study this reaction here. So CBr again. So this is the leaving group. This he will go here. Now we have, say, we can show 4 different groups are bonded to the central carbon atom here. So we can have on a wedge we can show a methyl group here, and say down, say CH2D deuterium. Then we can show on a wedge we are showing a methyl group here. Okay, so this central carbon here, this carbon is a stereogenic center, central carbon stereogenic center. So this is bonded to the leaving group Br here. Correct. Okay, now this is step 1 of the reaction. So this will be reacting with a general nucleophile. Let us see. So step 1 here, it will be, the leaving group leaves and a carbocation is formed here. So this carbocation is at the center here, C plus. Okay, now everything is same here, CH2, CH3. Correct. Now we have so this group we can put it here. on a wedge. We are putting that group there on a wedge, and this is a positively charged carbon atom here. So this is the carbocation here, correct? So this nucleophile, it can attack. This is our nucleophile here, correct? So this carbocation, it is a trigonal planar shape here. When it is a trigonal planar shape, the nucleophile has got a freedom. It can attack from either side here. Okay, it doesn't have any specific preference from where it should come and attack this carbocation here. So nucleophile can attack from either side. It can come from the left side or it can come from the right side here. Now, if it is coming from the left side here, so like this. So this is the difference between the Sn2 and the Sn1 mechanism here. Sn2 we have seen is only backside attack here. Nucleophile attacking from the backside, and there is inversion of configuration. That is Walden inversion, we have seen that. So here the nucleophile, it is attacking from the left side equally. That is with equal frequency it can do like this. See, it can come from here, it can come from here. That is the preference, there is no special preference here. Correct? It can attack from either side here. Okay, so let us see what is the kind of product being formed here. So Br minus, that is our leaving group. So it's a planar carbocation. Now, if it is attacking from the left side here, so what will happen? The nucleophile, it will be here, and U. This side it will be there. Correct? See, then and their groups we can put it here. You see, CH2D is there. Then we have on the wedge our methyl group. Then we have the ethyl group here. Correct? So this is one product being formed here. Then if it is attacking from the right side, what is the nature of the compound being formed here? It can attack from either side. There is no special preference. Correct? Therefore, we will be getting a compound of this nature, a product of this nature here. The nucleophile will be this side here. Okay. The rest of the things will be the same. CH2D here. Then we have that on the wedge. I will show roughly the reaction here. Okay, now we have this CH3, CH2. Okay, so this is our compound A, and this is compound B, and this is C. Okay, three products are formed here. Two products are formed here. That is from A. A is a starting material. That is a single stereogenic center is there. Correct? So it can give B and C here. Correct? So since the nucleophile is attacking from either side, the loss of the leaving group, that is a Br minus here in step 1, it will generate a planar carbocation. Most important point here is planar. Correct. It's a planar carbocation. You see, this planar carbocation, it is an achiral molecule. It is achiral. Okay, it is achiral. So attack of the nucleophile in step 2, it can occur from, say, either side to give two products A and B. B and C here. Correct. B and C are the two products being formed from A. Okay. Now let us see the B and C. Let us see what is the type of these products B and C here. So if you look at closely, B and C are, okay, they are different compounds here. They are not identical. They are different compounds. Okay, they have got a stereogenic center. Correct. They have got a stereogenic center. They are different products. And look very closely further. They are mirror images. Okay. So B and C are, they are stereoisomers. B and C are stereoisomers, and they are mirror images. What else? They are non-superimposable mirror images. Then they are enantiomers. Most important point. Okay. B and C, they are enantiomers. They are non-superimposable mirror images formed here. Okay. Now there is no special preference for the nucleophile to attack. It can come from either direction. Okay. Therefore, the B and C, it can be formed in equal quantities. B and C, that is in equal quantities or equal amounts of the two enantiomers can be formed here. It is a, what is the name of this compound? It is known as racemic mixture. That is B and C. It is a mixture of two enantiomers we are getting here. In an Sn1 reaction, the most important point, in contrast to the Sn2 inversion takes place, Walden inversion. Correct? In Sn1, a racemic mixture is formed here because there is no specific preference for the nucleophile to attack. So therefore, an equal amounts of two enantiomers, it is formed. That is a racemic mixture. When this process is known as racemization. Therefore, in an Sn1 reaction, Sn1 reaction proceeds with racemization here. Okay, racemization means it is the formation of equal amounts of two enantiomers from a single starting material. Correct? Then, Sn1 reactions proceed with racemization at a single stereogenic center. Correct? Now the leaving group, when the leaving group is bonded to a stereogenic center. So Sn1 reactions, it proceed with racemization at a single stereogenic center here. Got the point? This is the difference between Sn2 and Sn1 here. An important difference in stereochemistry here. Okay, now let us see a compound. How this racemization, I will just explain to you how it is taking place here. Say, now in a reaction of this nature here. So here we can say C, then we have a leaving group here Br, then a stereogenic center Ca3, then we can on a wedge we can show an ethyl group here. So this will be an example of a okay. So this is the stereogenic center here. So this is reacting with a neutral nucleophile here. This is a neutral nucleophile, important point here. So this will be an Sn1 mechanism. Let us assume the reaction is proceeding by the Sn1 mechanism here. Okay, now Br is the leaving group and H2O, it is the neutral nucleophile here. Loss of bromine, the leaving group. Correct? So it will give you a carbocation, a trigonal planar carbocation. And this nucleophile water H2O, it can attack from either direction. Okay, so let us see what will be the nature of the product being formed here. So let us draw the carbocation, how it will look like. I'll put it here. So this is C. Okay, Br is gone now. Correct? So this Br, it goes here. So step 1 of the reaction here. Okay, this step 1, what we are getting here, we are getting a carbocation here. Okay. So this is the step 1. We will be getting a carbocation, a planar carbocation we are getting here. Now we have N plus Br minus here. Correct. So this water, this is our nucleophile here with the oxygen, with a non-bonding pair of electrons here. So we will get two products here. What are the kind of products here? So because this water, this nucleophile, it can attack. We have seen it can come from this side or it can come from this side here. Two possibilities we have seen now. Now, two compounds we can draw here. Correct? So this will be, so left side attack and right side attack we can just show here. So this is our carbon here. So here we will be getting OH group here, OH2 plus. Correct? Water, it is getting attached here. Then we have the rest of the groups here. Okay. Then we have our Ca3, all intact. Correct? Now, this is our, this compound can be formed here. Then, and there can be a mixture here. Correct. It can attack from the other side, means it will be like this here again. We have C here. This OH2 plus, it will be this side. And this side it will be our other groups here. So like this, we can show, say we have the CH3 groups here. CH3 is there. Then we have the CH2CH3 here. So these are the two different types of enantiomers being formed here. Correct. This is the step 2 of the reaction here. Okay. That is the nucleophile water attacking from the left side and the nucleophile water attacking from the right side here. Because both the things are equally possible. Correct. So initial product of the nucleophilic substitution, it is the carbocation, positively charged carbocation. So no, this is the thing. First we are getting the carbocation which is reacting with the nucleophile from either direction here. Okay. So now in this one, what happens here? We can easily identify another step 3 here. Actually, the Sn1 mechanism is 2 steps here. Here, what is happening in step 3? A Bronsted-Lowry acid-base reaction is taking place here. That is very interesting here. That is first 2 steps Sn1 reaction. That is Sn1 is heterolytic cleavage of the CBr bond, and a new nucleophilic bond with the nucleophile is formed here. That is, there are 2 steps that are involved. An intermediate carbocation, that we know. That is 2 steps here. Here, in the 3rd step, when we are using a neutral nucleophile like water, this H2O plus, it readily loses a proton here. That is a ROH2 plus here. Okay, so this ROH2 plus, it will readily lose a proton here, and we will be getting a compound ROH. Correct. The final product will be like this. So overall process with a neutral nucleophile, it has got 3 steps. First 2 steps is constitute the 2-step mechanism, Sn1 mechanism. First 2 steps here. Okay. Now loss of the leaving group and attack of the nucleophile and all this kind of a thing. And the 3rd step, it is known as Bronsted-Lowry acid-base reaction here. So the Bronsted-Lowry acid-base, and we will be getting finally a neutral product here. So we will get a neutral product. This OH2 will become a product of this nature we will be getting here. Okay, COH, and we will have CH3, then CH2, and the other way around also. OH will be on the other side here. So this is the final product. It's a neutral product here. Ionic product will become neutral product because there will be a proton transfer reaction taking place here. That is Bronsted-Lowry acid-base reaction. So I have already given a video. You can go through that. Bronsted-Lowry acid-base reaction. So the proton loss here, and final product will be an OH group. Correct. In the same way, we can identify many reactions here. Say where the leaving group, it is replaced by OH group and all with a neutral nucleophile. Say for example, iodine. Now we have say CH3 here. Then we can have say CH2D. Correct. Then we can have CH2CH3. Something like this, some compound here. So if it is reacting with a neutral nucleophile water here, the iodine, it will be replaced by the OH group here. Straight away we can write, this is OH here. So this will be C. Rest everything is same here. And plus HI. Correct. So this is the kind of reaction. So this will be getting a racemic mixture. OH this side and OH on the other side will be getting a. So racemic mixture will be formed here. not a single product here. So initial product of the nucleophilic substitution with a neutral nucleophile, correct, ROH2, it will be losing a proton readily to form the final product ROH here. So let us see a compound of this nature now. See, like this. So we have it's a wedge actually, slightly it has become thicker. Say chlorine, correct. Then we can have another group over here, say methyl group here. So in this compound, now if it is reacting with water, so we will get a mixture here. Again, what is the kind of mixture? So here it will be, OH will be there on a wedge, like this. This is one product being formed, and another product will be here. The OH will be down the plane here, and CH3 will be above. This is a racemic mixture again here, plus HCl. Okay, so nucleophilic attack on the trigonal planar carbocation, it will be taking place in this fashion here. So it can attack from the both sides here, correct. So this is the stereochemistry of Sn1 reactions here, Sn1 stereochemistry. Okay, now next thing is very important point, that is the R group, the nature of R group, how it influences the rate of the reaction here. Very important point here, rate changes in Sn1 mechanism. So we will be dealing with in detail rate changes in Sn1 reactions here. Therefore, now R group here. Now we have, say, CH3X, that is a methyl. CH3X is there, that is a methyl group here. Methyl halide. Then we can have primary one, RCH2, say X, this is a primary one. Then we can have R2CHX, this is a secondary one. Then R3 CX, this is a tertiary one. Okay, primary, secondary, tertiary, that methyl one. This is the methyl one. Now, you see, that means the hydrogen atoms here in the methyl group, they are successively replaced by the alkyl group here. Okay, CH3X, then we are having one hydrogen gone and one alkyl group has come, R. And in the secondary one, two hydrogens replaced by two alkyl groups, and the tertiary one, all the three hydrogens replaced by three alkyl groups here. Now, as a number of R groups, the general principle here, as the number of R groups on the carbon atom with the leaving group, correct? The carbon atom with the leaving group, the number of R group increases, the rate of an Sn1 reaction increases. Therefore, increasing rate of Sn1 reaction. So this is the order of the reaction here. See, like this order. We can put an arrow here like this. So increasing rate of Sn1 reactions here. That is a tertiary alkyl halide. It will give an Sn1 reaction very, very fast here. Okay. That is, the number of alkyl groups keeps on increasing here. That means the rate of the reaction, Sn1 reaction, keeps on increasing. So tertiary alkyl halide, it will undergo Sn1 reaction very fast. A secondary alkyl halide, very slow. Correct. Now once we come to say methyl and primary alkyl halides here, methyl and primary alkyl halides, they do not undergo Sn1 reactions here. So this is another major difference between Sn1 and Sn2 here. Sn2, it is the other way around here. Okay, here in Sn1 reaction, the tertiary alkyl halides, they undergo Sn1 reactions rapidly, very fast. And the secondary alkyl halides, they react very slowly. And the methyl and the primary alkyl halides, they do not undergo Sn1 reactions here. Now the trend is exactly opposite to what we have seen in Sn2 reactions here. Okay, now how will you explain this thing? Very important points here. Okay, so explaining this, there are so many factors. We must examine the, say, the rate determining step here. Now the formation of the carbocation and the leaving group, the effect of the alkyl groups, and so many factors are involved here. Okay, we will discuss one after another here. Correct? Now, before we go to the important aspect of the carbocation stability here, we will be just seeing today. Then here the first, the Sn1 reaction, we will sum up the kinetics. It is a first order kinetics. Okay, the mechanism, it is two-step mechanism. Now stereochemistry, it is a trigonal planar carbocation is formed here, and racemization at a single stereogenic center. Okay, now identity of the R group, that is R group, the rate of reaction, it will be, say, R3CX here. So here the Sn1 reaction, it will be the fastest here. It is followed by, say, R2CHX. Then it is followed by RCH2X, followed by methyl, RCH3X here. Correct. So this is the order of the reaction rate here. Okay. This is how the alkyl groups, number of alkyl groups on the carbon atom with the leaving group, it is how it is influencing the rate of the reaction here. Correct. So the rate will be like this only. Now we can see the stability of the carbocation. Briefly, I will just cover today. Very important thing. The carbocation is the most important thing here. That is the intermediate here. That is the stability. You see, any ion, it will be getting stabilized, whether it is a positive ion or a negative ion, whatever it is. The stabilization or the stability of the ion depends upon the electron delocalization. How the charge is getting spread, whether the negative charge is getting spread over a larger volume or the positive charge is getting spread over a larger volume. It all depends upon that point. That is a fundamental principle here. The stability depends upon the how fast or how far this charge is getting spread. Correct. Now let us examine here the stability of carbocation. Briefly, the most important thing is the carbocations here. We have the methyl carbocation, Ca3 plus here. Let us see the stability, how it will be. Now this is the RCH2, that is the primary one. So this is methyl. The order of the stability we can see here. This is the primary one. Then we have R2CH secondary. Then R3C. Correct. So tertiary one. So now as the number of R groups on the positively charged carbon atom, it increases, the stability of the carbocation increases. Correct? Just like the rate of the reaction we have seen Sn1 reaction, as the number of R group increases, the rate of the reaction increases. In the same way, the number of R groups increases means the stability factor. The stability of carbocation increases. So what are the factors responsible for this? Increasing stability here. Now stability means what? It is, we don't mean to say that it is highly stable, it can be isolated, nothing of that kind. It is a relative stability we mean to say. That is the tertiary alkyl halide, it is more stable compared to the secondary one. And the secondary one is more stable compared to the first one. And everyone is unstable. All these carbocation intermediate, they are very, very unstable, highly reactive species. And it cannot be isolated or anything of that kind. Okay. Therefore, the tertiary carbocations are too unstable to isolate here. Correct. But they are more stable compared to the other one. That is the relative stability we mean to say here. Now, the reasons for this thing. Very briefly, I will tell you reasons why this is more stable here. Important point. One is because of the inductive effects here. So, inductive effects means what? That is a donation or withdrawal of electron density along a sigma bond. That is, if we have a sigma bond, electron density is withdrawn or electron density is donated. So we have seen a negatively charged, say, a negative electron negative atom like a chlorine, bromine, and all this kind of a thing. They are all, they withdraw these electrons here. So inductive effects are, they are electronic effects we can say. They are electronic effects that occur through sigma bonds here. That is electron withdrawing inductive effect. We have seen that. And electron donating inductive effects are there. Correct. So the more electronegative atoms, they stabilize a negative charge here by electron withdrawing inductive effect. That is, a negative charge is stabilized by a more electronegative atom. How? By electron withdrawing inductive effect here. Okay. Now, to stabilize a positive charge, we need electron donating groups. They are needed here. That is, two types of inductive effects we have seen: electron donating, electron withdrawing here. Correct. Now, alkyl groups, for example, alkyl groups are electron donating groups here. Okay, alkyl groups are electron donor groups. That will be stabilizing the positive charge here. That is, electron donor groups, we can say it is said, if we say, it will stabilize a positive charge here. We can say Y plus. Correct. So, electron withdrawing groups here, W. So, it will be stabilizing a negatively charged ion here. So, alkyl group with several sigma bonds, it is more polarizable. Correct. Than a hydrogen atom. And you see electron donor groups we have seen said here. So it will stabilize a positive charge. Correct. Now electron withdrawing groups, it will stabilize a negative charge. So alkyl group with several bonds, several sigma bonds, we can say. Several sigma bonds, alkyl groups. What will happen? It is more polarizable than a hydrogen atom, single hydrogen atom here. And therefore, it will be able to donate more electron density. So, an alkyl group, R group here. R group is an electron donor group here. It is donating here. Okay, therefore, this inductive effect we can see in the case of, say, this is a methyl carbocation here. It doesn't have any alkyl group here, to stabilize here. Now, we can see if you got an R group here, what will happen? R group. So this R group, it will supply electron density here like this. Correct. So there are several R groups are there means, what will happen? Electron density, R groups, if you successively, if you are replacing the hydrogen atoms in the methyl with the the positive charge, it will be more dispersed, correct, on the electron donor R groups here. And the carbocation, it will become more stabilized here. So here, now, if you have another R group here, this is the inductive effect. Electron donating inductive effect, we call it now. So, see, like this we can show it here. Correct, like this, it will be spread over a larger volume here. Like this we can show. Correct. So increasing number of electron donating R groups, increasing carbocation stability here. Correct. Understood. So alkyl group with several sigma bonds, it is more polarizable than a hydrogen atom and more able to donate electron density here. Thus, R group successively, if you keep on replacing the hydrogen with R groups in the Ca3 plus here, correct, the positive charge, it is more dispersed on the electron donating alkyl, R groups here. R groups are all electron donating groups here. Correct. So this is how it is getting stabilized here. Now, another important point which I just want to bring to your briefly discuss here before we conclude. Hyperconjugation. What is hyperconjugation? Even hyperconjugation stabilizes a carbocation here. Hyperconjugation means, you see, now we have seen the observed trend. What is the trend here? The stability of the carbocation here. A tertiary carbocation, it is more stable than a secondary carbocation, and compared to a primary carbocation or a methyl carbocation. That is tertiary carbocation, the stability is much more here because the positive charge, it is delocalized over more than one atom here. That is hyperconjugation. I will just discuss. So that means the spreading out of the charge here. Okay, spreading out of the charge, the positive charge here by the overlap of an empty p orbital. Okay, with an adjacent sigma bond. It is called hyperconjugation. Correct? Now, how from where we are getting the p orbital and all this kind of a thing, overlap? It's simple. We have a carbocation. Carbocation, we know. Carbocation, it is an sp2 hybridized carbon atom. Correct? Therefore, one p orbital vacant here. This p orbital, vacant p orbital. Correct? sp2 hybridized carbocation here. There is a vacant p orbital here. This p orbital, vacant p orbital, it can overlap with an adjacent sp3s hybrid orbital or a sigma bond here. Correct? I will just briefly, I will tell you. Say, for example, this CH4 methane, the carbon is sp3 hybridization. Correct? sp3 hybridized. How it is forming here? This carbon sp3 orbital here. This sp3 orbital, it is overlapping with a 1s orbital of the hydrogen atom here. sp3 1s. That is how this carbon hydrogen bonds are formed here. Correct? So this orbital, this is forming a sigma bond here. So this sigma bond orbital adjacent to the vacant p orbital, there will be an overlap. That is called hyperconjugation. That is the spreading out the charge by the overlap of an empty p orbital with an adjacent sigma bond. It is called hyperconjugation. So it has got another name. Hyperconjugation has got another name here, what is called no bond resonance. It is also known as no bond resonance. That is resonance, that is the delocalization of electron density either from a non-bonding electron pair or from a pi bond that we have seen there. So no bond resonance. So it is a variant of a resonance theory here. So according to this theory, that is electron delocalization, it can occur by the parallel overlap of p orbitals with a hybrid orbital participating in a sigma bond. That is adjacent sigma bond is there. There should be an adjacent sigma bond here. Then only it can form here. Correct? So it is called a no bond resonance. No bond resonance here. So I will briefly tell you. I will not go very much into detail here. So let us see how it is. Now, the charge cannot be spread here. So all ions, the spreading of, the charges, it can happen only with the help of a delocalization. The charge can be stabilized by only delocalization, correct, of the so we can say so Ca3, a carbocation Ca3 plus, correct. Then we can have this is methyl carbocation. Then we can have an ethyl carbocation. Two carbocations. Let us examine how it will be. Okay. So the methyl carbocation, we can draw it in this fashion here. So this is the vacant p orbital here. Correct. Plus charge. Okay, so this is the methyl carbocation here. Then there can't be any orbital overlap here with a vacant p orbital here, because adjacent there is no carbon atom. So sp3 hybridized carbon atom, it is not there. So this CH3 carbocation, it cannot be stabilized by hyperconjugation here. But if you see, say another CH3 twice CH plus or CH3 ethyl carbocation or so this carbocation, say we can see CH3 twice CH plus, how it will be. So so we have this C. So this is the p orbital here, vacant p orbital here, adjacent vacant p orbital here, correct? Now here there is another carbon here. Okay, so this will be a CH3 group here. So we can have another CH3 group. In this CH3 group, here we have a bond here. That is a sigma bond is formed with a hydrogen atom here, correct? Therefore, there will be an orbital here like this. Now, these carbons here, hydrogens here, okay. Here what is happening? So there will be an overlap here. So this thing can be, this will have a small lobe here also. Okay, there can be an overlap here. So this is the sigma bond here. So this sp3s orbital here, that is this carbon sp3, then hydrogen 1s. This orbital here, there can be an overlap from this side here. Like this, it can overlap here. So this will stabilize the positive charge on the carbocation here, correct? This is known as, this is a positive charge here. So overlap of the carbon hydrogen sigma bond, this is the carbon hydrogen sigma bond with the adjacent vacant p orbital here. Okay, it will stabilize the carbocation here. So this is the principle of what we call hyperconjugation or no bond resonance here. So both carbocations, it will contain an sp2 hybridized carbon atom. Both are, having the geometry trigonal planar with a vacant p orbital here. It will extend above and below the plane, correct? In the methyl CH3 plus, what happens here? There are no adjacent CH sigma bond with which the p orbital can overlap here. But in the other case here, there are adjacent, adjacent CH bonds are there here, correct? This overlap delocalizes the positive charge. Delocalizes means the charge is getting spread over a larger volume here. Therefore, the carbocation, it is getting stabilized. So this is hyperconjugation here. Now, the thing is, you see, both the carbon, this thing, we can say the C1 and C2 here. So there will be, say, restricted rotation. Rotation will be there around a single bond here. Therefore, each sigma bond here, carbon sigma bond, carbon hydrogen sigma bond, it can have overlap. It can overlap with the vacant p orbital here. Therefore, the positive charge, it will be getting stabilized. So this is the no bond resonance. Correct? I will not go too much into detail here because the carbocation, it is stabilized with the help of inductive effects. There are two theories there, inductive effects and hyperconjugation. Okay, so because the hyperconjugation means this thing, the sp3s orbital here, okay, containing the bonding electrons in the carbon hydrogen bond adjacent to the sp2 hybridized carbon atom. It can overlap. It's a orbital overlap is involved here. It can overlap with the unhybridized empty p orbital here on the sp2 hybridized carbon atom here, and share the bonding electrons. What the point? That is, the sp3s orbitals, it contains the bonding electrons in the CH bond here, carbon hydrogen bond here. A sigma bond is formed here, correct? It is adjacent to the sp2 hybridized carbon atom. So these orbitals can overlap. with the unhybridized p orbital here, correct, on the sp2 hybridized carbon atom. And the bonding electrons can be shared here. Now, sharing electrons in this manner, it is called hyperconjugation here. So, as the number of alkyl groups keeps on increasing here, the positive charge can be spread over a larger volume compared to the methyl carbocation here. Therefore, the stability of the carbocation increases as the number of alkyl groups here keeps on increasing. This is one way of explaining this. So, thank you very much for listening.